Let's take a look at another model, this one involving exponential decay. The radioactive isotope 226Ra has a half-life of 1,620 years. Generate a function n of t that models the amount of 226Ra present over time if the initial amount is 5 grams. All right, so we're going to be dealing with half-life, which means exponential decay, which means we can use our general form for exponential decay, our exponential decay model. That would be y equals a e to the negative bx, where b is greater than or equal to 0. Now, because we're trying to come up with a amount function, n of t, as a function of time, instead of y, I'm going to use n of t, and instead of x, I'm going to change the variable x to t to represent time. All right, so n of t is equal to a times e raised to the negative bt. In order to complete this model, we must solve for the constants a and b, right? We need to figure out what a is, and we need to figure out what b is. There are two unknowns in this equation. Again, remember, we don't have to solve for e. E is already a number, and we don't have to solve for t because t is a variable time. T is your independent variable, n of t is your dependent variable. Well, how are we going to do that? Let's think about some of our given information. All right, we know that n of 0 is equal to 5, right? The initial amount is 5 grams. This means that if I plug in 0 in for t, I have to get out 5. So let's do that. That would give me a e to the negative b times 0 is equal to 5. Again, plugging in 0 for t gives me out 5. Well, why does this help me? Well, this gives me e raised to the 0 power. And e raised to the 0 power is 1, which tells me that a is equal to 5. Now we have solved for one of our constants. We can now plug that into our expression. We're getting there. N of t is equal to 5 times e raised to the negative bt. So now all we have to solve for is this constant b. What else is given information? Well, we know that this radioactive isotope has a half-life of 1,620 years. That means if I plug in 1,620 in for t, what do I have to get out? Well, I have to get out 2.5. I have to get out half of what I started with, right? Every 1,620 years, I will have half of what I had previously. So half of 5 would be 2.5 grams. So let's plug this information into our equation now. This would be 5e to the negative b times 1,620 is equal to 2.5. Again, plugging in 1,620 has to give me out 2.5 grams. Well, what we have just done here is generated an exponential equation. And how do we solve exponential equations? We begin by isolating the exponential quantity. We can divide both sides of the equation by 5. This gives me e raised to the negative 1620b is equal to 1/2. Now, we have the exponential quantity isolated. We can now do the inverse operation of this exponentiation to help us solve for b. To do so, we take the natural log of both sides. The natural log of e raised to the negative 1620b is equal to the natural log of 1/2. On the left-hand side, these inverse operations are going to cancel each other out, leaving us with negative 1620b. And on the right-hand side, because we have division inside of a log, we can expand that into subtraction of two separate logs. This would be the natural log of 1 minus the natural log of 2. The reason we want to do that here is because the natural log of 1, well, that's going to simplify into 0. Excuse me. So we have negative 1620b is equal to negative ln2. And finally, to solve for b, we can divide both sides of the equation by negative 1620, giving us b is equal to the natural log of 2 divided by 1620. Now that we have solved for both constants a and b, we can plug those into our function. Here we have n of t is equal to 5e to the negative ln2 over 1620 times t. Again, remember our general form here. We had n of t is equal to 5e to the negative bt. Don't forget about putting that negative in front of the b. Negative 1 times b. All right, so there is our model, but notice it's a little bit ugly. Okay, n of t is equal to 5e to the negative ln2 over 1620 times t. Let's do some algebraic manipulations to make this look better. So we have 5e to the negative ln2, and I'm going to multiply that by t over 1620. Notice instead of dividing ln2 by 1620, I can divide t by 1620. Okay, it doesn't matter where I do that division. And now we can recognize here I have multiplication in an exponent. That's the same thing as exponents raised to exponents. So this is 5e to the negative ln2 raised to the t over 1620. Again, exponents raised to exponents, we would have multiplication of those exponents. So why does that help me out? Well, let's think about what this means here. Again, negative exponents give us a reciprocal. That would be the same thing as 1 over e to the ln2, right? Because that's a negative exponent, I can put it in the denominator of a fraction. And e to the ln2, well, again, I'm exponentiating a natural log. Inverse operations, those cancel out, leaving me with n of t is equal to 5 times 1/2 raised to the t over 1620. All right, so hopefully this looks a little bit better to you guys. And for those who have taken chemistry, this may look familiar. This is our half-life formula. All right, this is a formula that you might want to write down and put into your notes. It will make any half-life problems much, much, much easier. Okay, instead of going through this whole process of generating the formula, we can just start off with this format here and plug and chug. All right, so half-life is equal to, we have n of t is equal to n naught, n subscript 0, that's the starting amount, the initial amount, times 1/2 raised to the t divided by the half-life. So now that we have our formula, how much remains after 10,000 years? Round to 3 decimal places. Well, all that means is we need to plug in 10,000 in for t, evaluate n of 10,000. That gives us approximately 0.069 grams. All right, so there an example of exponential decay. And two ways to start this off. You can start off with our general form of exponential decay, or if it is more specifically a half-life problem, you can use this half-life formula.